What if an AI could think dozens, even hundreds of steps into the future, not just one or two? And what if it could plan out a whole complex series of actions all at once, instead of just plodding along step by step? Well, today we're diving into some really incredible research that tackles one of the biggest hurdles in artificial intelligence: long-term planning.
I mean, really think about it. How do you actually teach a machine to see ahead? Not just to react to what's right in front of it, but to truly anticipate, strategize, and follow through on a plan to get to some far-off goal. It's a question that's kind of stumped researchers for years, but a new approach might just have cracked the code. And that answer comes from this paper right here: Parallel Stochastic Gradient-Based Planning for World Models. It's a team-up of some brilliant minds from UC Berkeley, Meta Fair, and NYU. They've cooked up a new method designed to solve these super complex, long-horizon tasks, and honestly, it's a total game changer. So to really get what they've done, here's our game plan. We'll start with the big problem they're trying to solve. Then we'll get into the 3 big ideas behind their solution. We're going to peek under the hood at the planner itself, check out the pretty amazing results, and then talk about why any of this actually matters for the future of AI. All right, first up, let's tackle that core challenge. In the AI world, they call it the long horizon problem. And it's simple, really. The further an AI tries to plan into the future, well, the harder it gets. But why is that? To get it, we first need to talk about something called a world model. So a world model is basically an AI's internal simulator. It's like this little physics engine running inside its own head that's learned the rules of its environment. It lets the AI imagine, okay, if I do this, then that will probably happen next. It's the AI's imagination. But here's the catch. Those predictions, they're not perfect. The old way of planning is to simulate one step, then the next, in a long chain. But every tiny little error, no matter how small, gets carried forward and actually gets bigger over time. So across 50 or 100 steps, that tiny wobble at the start turns into complete chaos at the end, and you get a plan that's totally useless. And this slide, this visualizes another huge problem: getting stuck. See that jagged landscape on the right? Think of that as all the possible plans. A simple planner is like a hiker trying to find the lowest valley. It can easily get trapped in one of those little dips, thinking it's found the best solution, when the real best plan, that super deep valley, is just over the next hill. It gets stuck in a local minimum.
So how do you fix this, right? How do you smooth out that landscape and stop those dominoes from falling over? This is where the paper gets really clever with its solution, which is built on 3 big ideas.
They call their method GRASP. It stands for Gradient Relaxed Stochastic Planner. And that name actually tells you a lot. It combines the mathematical precision of gradients with a more flexible or relaxed way of looking at the world. Okay, so here are the 3 core innovations. And this is the important part. First, GRASP decouples the whole planning process. Instead of that one-by-one domino chain, it basically lays out all 50 future steps at the same time and optimizes them all in parallel. Second, it injects a little bit of strategic randomness or noise. This is what helps it jump out of those little valleys we saw before and find better solutions. And third, it uses something called gradient cutting. Think of it like noise-canceling headphones for the planner. It just tunes out all the confusing, unreliable signals from its world model so it can focus only on what really matters. This makes the whole thing way more stable. So let's pop the hood and see how these ideas come together to build a totally different kind of planner. This is seriously like going from a windy single-lane country road to a massive multi-lane superhighway. And this diagram just illustrates the difference perfectly. The top part, that's the old way. One state leads to the next, which leads to the next. It's slow. It's sequential. But the bottom diagram, that's GRSP. It's considering all those virtual states in the middle at the exact same time, optimizing the entire path from start to finish all at once. It's a completely different way of thinking about the problem. And the advantages of going parallel, they're huge. Where serial planning is slow and gets stuck all the time, GRASP is fast and explores way more possible solutions. But the most important thing is, serial planning just falls apart when you try to look too far ahead. GRASP's entire architecture is built from the ground up to be stable and robust, no matter how far into the future it needs to plan. So, of course, a fancy new architecture sounds great on paper, but how does it actually perform? How did GARSP do when they put it head-to-head against some of the other top AI planners out there?
Well, the results kind of speak for themselves. On a really complex task that required a 50-step plan, Grasp had a success rate of over 43%. That's way better than the other planners. But look at the time, just 15 seconds. It's 5 to 6 times faster than its competition. It's not just a little bit better, it is massively more efficient.
And this wasn't a fluke. Across a whole bunch of different tests, they saw the same pattern. Grasp was delivering up to a 10% higher success rate, and it was doing it using less than half the computer power. Getting both higher accuracy and more speed, that's pretty much the holy grail for AI planning. And this image shows why that matters. This is what they call a non-greedy solution. A simpler planner would just try to go straight for the goal, get stuck on that obstacle, and then fail. But Grasp is smart enough to see that it actually needs to move away from the goal for a second, to get around the barrier and then find a winning path. This is exactly the kind of intelligent, long-term thinking that's been so hard to achieve until now. So what's the big picture here? Why does having a faster, more stable AI planner actually matter in the real world? Well, the potential applications are just huge. We're talking about robots in factories that can plan out really complex assembly tasks, or self-driving cars that can see and plan for traffic situations hundreds of feet ahead, not just a few car lengths. You could have super realistic surgical simulators for training doctors, or even video game enemies that are genuinely strategic and unpredictable. The authors themselves really sum it up best. They say their approach creates a planner that stays robust, even as the plans get longer, finds those clever, non-greedy solutions, and does it all much faster. By tackling the long horizon problem, they've really unlocked a whole new level of what AI is capable of. And that leaves us with a pretty fascinating final thought. For years, we've been building AIs that can react to the world. Now, we're building AIs that can truly plan ahead. So the question isn't really if they can think ahead anymore. The real question is, with this incredible new power, what are they going to help us build next?